Assalamu alaikum. Welcome, dear students, to our last lesson in Part 2 Waves, Chapter 11 about the refraction of light, Part 1. At the end of this chapter, you will be able to define the phenomenon of refraction of light, to define the index of refraction, to explain the behavior of light when passing to more and to less optically denser medium, to state and apply the laws of refraction, Descartes' Snell's law, to define the limiting angle of incidence, or what we call a critical angle, to recognize the conditions of total internal reflection. In this video, we are interested in the first three objectives. Let's review together the ideas of Chapter 8. A reflection of light is the bouncing of light in the same medium when it hits a reflector, as you can see in this animation. The incident and the reflected waves have the same frequency since they are generated from the same source, the same speed since they are propagating in the same medium, and both of them have the same wavelength based on the relation V equal lambda times F. In reflection, the angle of incidence I is equal to the angle of reflection R. Let's start by observing the following figure. Here we have a transparent sheet of glass. What happens to the direction of light's propagation as it emerges through glass and as it leaves it? We can notice the change in the light's direction in both cases. Also, let's observe the pen half immersed in the container filled with water. We can see the edge of the pen due to the light coming out from it. But this light is passing between two transparent mediums, water and air. Thus, we will not see the actual position of the pen since light changes its direction in this case, and the pen appears to be broken. These phenomena are actually due to the refraction of light, which is the passage of light from one transparent medium into another where light propagates with different speed. And from the previous chapter, we have learned that refraction is not necessarily accompanied with a change in the light's direction. Let's move now to our second objective. Observe the following two figures. In the first one, light strikes the interface air-water, whereas in the second one, light propagates from air into glass. We have learned before that light changes its speed when traveling in different mediums. So, do you think that the refracted rays will behave the same in glass and in water? Let's see. We can clearly notice, other than the change in their speeds, in glass the refracted ray bends more toward the normal. Therefore, the change in speed may lead to a change in the direction and in the wavelength of the refracted wave. In this case, when light travels from air into glass, it slows down more than it do when traveling from air into water. That's why, in the second figure, the refracted ray bends more toward the normal. Don't forget that light is an electromagnetic wave that propagates with its highest speed in vacuum. This means that the speed of light decreases as the density of the medium increases. In other words, the speed of light in gases is greater than its speed in liquids is greater than its speed in solids. Then, whatever is the speed of light in a specific medium, for example, it is 229,000 km per second in ice, and it is 197,000 km per second in glass, it is for sure less than its speed in vacuum, which is denoted by small c, where c is equal to 300,000 km per second. So, as the light passes from air into any other medium, its velocity of propagation decreases, and this diminution depends on the medium itself. That's why in optics we need to define a physical quantity n, called the index of refraction, where each medium is associated with a well-defined value of n, and where n is the ratio of the speed of light in vacuum to its speed in a given transparent medium. Note that since v is smaller than or equal to c, then n equals c over v is greater than or equal to 1, then n is equal to 1 in vacuum and in air, and it is greater than 1 in all other mediums. Also note that the index of refraction is unitless. Let's have a look on the following table. The index of refraction of vacuum is 1. The index of refraction of air is approximately equal to 1. N of water is 1.333. Another example, N of plexiglass is 1.49. You are responsible just for memorizing the index of refraction of air, which is approximately equal to 1. Otherwise, the index of refraction will be given for you. Let's practice now by solving the following application, but before we start, please pause the video and try to solve it by yourself. Knowing that the speed of light in vacuum is c equal to 3 times 10 to the power 8 meter per second, its speed in air is approximately equal to c, and its speed in water is equal to 2.25 times 10 to the power 8 meter per second, you are asked to calculate the index of refraction of air and that of water. Applying the formula, index of air is equal to the speed of light in vacuum to its speed in air, which gives us c divided by c, which is equal to 1, and don't forget that the index of refraction is unitless. Similarly, by applying the formula, we obtain that the index of refraction of water is equal to 1.33. Now you are asked to calculate the speed of light in a glass, where the index of a glass is equal to 1.5. Using the formula, the speed of light in a glass is equal to c divided by the index of a glass, which gives us 3 times 10 to the power 8 divided by 1.5, which gives us that the speed of light in a glass is equal to 2 times 10 to the power 8, and don't forget to mention here the unit, which is meter per second. Always keep in your mind that between two transparent media of different indices, the one with the larger index of refraction is called more refractive medium, or an optically denser medium. Also, the one with the smallest index of refraction is called less refractive medium, or less optically denser medium. Now let's explain briefly the behavior of light when passing to a more optically denser medium. As light passes to a more refractive medium of higher index of refraction, it slows down since n and v are inversely proportional. And from what we have learned in chapter 8, the refracted rays bend toward the normal in this case. On the other hand, when light travels to a less refractive medium of smaller index of refraction, it speeds up and the refracted rays bend away from the normal. Now let's summarize the ideas of this video. The refraction of light is the passage of it between two transparent mediums where its speed changes. In optics, each medium is characterized by its index of refraction n, where n is equal to c divided by v, which is always greater than or equal to 1. Note that n is unitless, and the index of air is approximately equal to the index of vacuum, which is equal to 1. As light passes to a more refractive medium, it refracts toward the normal, and as light passes to a less refractive medium, it refracts away from the normal. This is the end of part 1. Thanks for your attention.